As was on display in yesterday's common sessions, the makerspace movement is rapidly becoming ubiquitous throughout our culture. Our group desires to think through how to leverage, both strategically and thoughtfully, the multiple facets of the makerspace movement, its culture, its value, its technology, and its accessibility to enhance engineering education in a thoughtful manner that includes, supplements, and transcends the classroom. Our title, Thinkers, Tinkers, and Engineers, Making Leonardos for a New Millennium, borrowing our second reference to Leonardo here. But our iconic reference to Leonardo is designed to capture the idea of the engineer as an integration of creativity, deep active curiosity, theoretical rigor, and prolific productivity. This type of engineer would be able to approach complex problems with creative solutions, being able to synthesize theoretical rigor with a tactile and practical understanding of the physical artifact represented by equations in class. The need for this emerges from a growing population of engineering students entering our programs who have been culturally pushed toward engineering simply because they're very, very good at math and science. That unlike previous generations of engineering students, they did not grow up taking apart their family car, they did not make crystal radios, that they weren't involved in all sorts of hands-on projects that pushed them towards the College of Engineering. At the University of Colorado, where I teach, we started a wild major 20 years ago called Open Option, and it had 6 students in it who didn't know which of the engineering fields they were wanting to go into. This last year's entering class was over 40% open option, who had no idea of what an engineer was, let alone which engineer they wanted to be. One of the things that we talked about is how to make the maker movement relevant, not only in the curriculum, but in co-curricular and non-curricular activities. This is what we just said. We can't assume today's students are able to solve complex problems and all of this. And how we might do this for a new millennium. But I wanted to talk briefly about the non-curricular projects. I live in a residence hall, and I have with my family for the last 7 years. I have 223 extended college student roommates who live right outside my door. And we're very much about creating projects that have nothing to do with the classroom. Eitan Sher, a student here, was a design superstar. He made Rubik's Cubes from scratch before he arrived. He made, by the time he graduated, a 24-sided one that a Chinese toy company bought. And I went to him at the end of his junior year and said, Eitan, I have a $10,000 budget for you if you can make a mechanical model of the solar system. Mechanical, not electronic. It has to function accurately. It has to include at least 10 other students, and it has to last for 150 years. You have to make it from scratch. So material, design, and all of this. And this is the product of this. He had a team together. These all started as brass slabs, and they milled these and all of that. And it was just one project, and they collectively put in over 2,500 hours for this and got no credit for it. And it now hangs in the ceiling of Andrews Hall where we live. We put out things like a 1928 phone, which is a wood phone with a wine thing on the side, and say we want 5 proposals in the next 3 months of how to make this the front desk phone with all the same functionality as the current modern front desk phone, and we will fund and budget whatever proposal wins. And we're constantly in the business of doing projects like this that students embrace and take on. I'd like to turn it over to Amy now, my esteemed colleague from the state of Illinois.
Well, thank you. And I had the distinct pleasure of then having Eitan as a graduate student. So while this presentation is not all about this student, it's really exciting to be able to see the impact that living in an environment like that can have on somebody and how they bring that to the space that they're working in. So one of the things that we talked about with our group was what is the ecology of the engineering lifestyle, and how do we create that sort of lifestyle? So Eitan came from this residency situation and moved into a small cohort-based master's program with a studio where all of the students are advised to live very close by because most of them think that they'll be getting very little sleep during the project. We do all sorts of team-based work, and it's hands-on work. So that's really sort of their maker space. And so a lot of the conversation that we had was also about the importance for this idea of either a studio, like art students would have, or a maker space as really a third space for the engineer and others on campus who are interested in hands-on problem solving. So this is an example of one of our spaces at Northwestern. And in our, let's see, we'll come back to that one. So it takes a lot of effort also to curate the community here. It requires a balance of both student-led effort and a fair amount of support. I think Maria yesterday was giving us a great statistics and detail about the design kitchen and the staff that they have. I'd be happy to talk with anybody about the Siegel Design Institute and our staff, but there's really a balance between the faculty, the students, and then other sort of support that's required to make those spaces effective and to make the students and the faculty really feel like that's a place that they can go and work together. And it's critical that there be connections to the curriculum and opportunities for co-curricular engagement throughout. So at Northwestern and DTC, which is our freshman design course, it's a course that's taught by, and I should probably do a shout out to my dean here, who is both an artist and an engineer. So he really supports development of these types of courses. But the freshman design course at Northwestern is taught jointly by a faculty member from our School of Arts and Sciences and a faculty member from engineering and from any aspect of any department in engineering. It's a very hands-on based project course where the students are working on client work and working in teams. So it's really critical that that work, whether it's high fidelity prototyping or in the low fidelity prototyping, be connected to the curriculum in really meaningful and effective ways for everybody involved. So it's great to talk about all of these things that can come out of having these maker spaces, these third spaces where they're a home away from home from our engineering students. But lest you think that we are not a critical thinking group, we also wanted to talk about the problems. Who does it? How do we pay for it? How do you get champions? What's the value proposition going in? Who funds the construction? What kind of hours do you have? How do you trust students? What about students' fear of being lame? All of those different concerns that may go into development of a space like this and creating that kind of vibrant community. So with that, I'm going to pass it over to Micah to talk a little bit about the help that we need from FOEE.
So there's some concrete things that we were thinking in a generative fashion, trying to come up with ways in which faculty or as a group we could help each other. And so having experiences as faculty where we go into a makerspace, have some motivation or allowances to make that happen, some way in which us as faculty can rotate through like a co-op experience of bringing our experience to industry and bring that know-how and context back into the classroom. I think with NAE asking for help of having a design challenge at different levels in freshman, sophomore, junior, senior, graduate school to help facilitate the context of how making and engineering can be across those things. We're thinking of, in the culture piece, thinking about instead of going Greek, going geek and supporting the engineering culture. And then we're starting to think of, generatively about how to bring that kind of engineering culture and extend it past the classroom to include themed housing or faculty and students making together in dorms and in student life. So with that, thank you. These are the people in the team, and then we ask and then open to your questions.
I'll start. What's the largest group size you ever recommend for your student-based projects? 1, 2, 3, 4. Okay. Yeah. 3, 4. We were 9 at one point, so thank you. And we also found, just in some of the self-reflection, if we could take a moment for metacognition here, one of the other things that we found was once we actually started doing something, like writing things down, the ideas came together much more quickly. And so we always, I think every single one of us works in a capacity where we encourage our students to have a bias for action. And we didn't start like that out of the gate, but we caught up. So, questions?
Letting people warm up, but I just want to support the idea of a maker in residence. I can think back to my freshman year and the making that was happening in my dorm room. That guy is now a PhD and founded one of the MakerWorks open lab spaces at MIT, and just being there. So maybe not like a themed residence hall, but like if you could have a maker resident in all the dorms, that would be really amazing for students to just like on their free time at home, drop by their office and already have these tools there. It'd be awesome.
I really like the whole maker idea. I'm old enough that I actually did tear apart old radios and TVs and stuff like that, yet I became a chemical engineer. And one thing I struggle with when I hear all this discussion, I see how this works for mechanical engineers. I really struggle with how do I do something similar for my chemical engineering students? What experience is equivalent for them?
So that question came up, but we didn't really have, I think, a coherent answer. Was there?
I don't know.
Yes, we talked about that because I'm a chemie and I'm concerned about how do we take that and incorporate it in so that all the engineering disciplines can make use of this. And we really don't have an answer to that. You know, if anyone here has ideas, that would be great to have these shared. You know, but yeah, I think one thing that we have discussed is that even with chemie, there are areas where you have overlap, for example, in controls. You know, you have overlap with electrical, mechanical, in certain areas. And so there are some areas where I think you can immediately make use of that. But it'd be nice to see some broader application of that as well.
And there was one area other than Breaking Bad where that would come in, which was synthetic biology. So that is a community that already has a maker movement. And so which is scary sometimes, maybe, and there is a culture of that, and so that's possibly something that would work.
Virginia Davis, Auburn University. So I think there is definitely a challenge in many ways to hands-on chemie projects, particularly early stage and having students make things. And so we have a freshman design project where they take a fuel cell and they make a car, and they are now, almost all the teams want to 3D print their car bodies. So the project, because it's a soy fuel cell, actually comes down to math and mechanical engineering factors, not the chemical engineering factors, but ties into chemie car team. And interestingly, there was funding available for student groups to start something, and it was the chemies who got funding for creation of a student lab for 3D printing, which is now advised by an industrial engineering professor. So it's small, just 2 units, but it was the chemies who started it. So I wouldn't count out the chemies. I think the students have ideas on how they see to use it that maybe we wouldn't even naturally think of. And polymers and a lot of these other materials aspects are very much chemie/materials disciplines.
One more question.
Just wanted to add to your comment for a second. I have seen amongst chemie students a great deal of interest in 3D printers because 3D printers are essentially materials processing systems. They treat materials at temperature, they extrude materials, they do all the things that the chemical engineers have to know. So in their case, they might be more interested in tinkering with ones that you can actually control the parameters of. and see what comes out the other end, and then be able to test that material. So that's maybe a way that you can work that into maker spaces.
He's a chemist. He's going to give us the answers.
I'm a mechanical engineer, but one project